Hello, chemists. Let's talk about some shapes. So I'm going to go to my notes here, and we're going to talk about molecular geometry, and we're going to separate it into two parts called families and shapes. And those are jolly terms. But mostly we're just interested in the geometry and the angles around individual atoms and then overall shape for the molecule. So molecular geometry is the general shape of a molecule, well, of course, determined by the three-dimensional positions. The first theory that we're going to talk about is something called valence shell electron pair repulsion model. So that's VSEPR. And it's really good at predicting the shapes of molecules. And it also is really good about predicting angles of molecules. And so this is the thing that I have in your reference for you. So if you want to look it up. And this, though, those two are not in your reference sheet, but the rest is. All right, and we're going to work through each one of those, but I'm going to go through the whiteboard. And we are going to talk about, let's see, how come this is small? Nothing. Okay, we are going to talk about the different types or the different possibilities. So valence shell electron pair repulsion theory is talking about electron pairs and how they repel each other. Because if you put electrons next to each other, well, they do not like each other, and so they will repel, and they will repel to make the most of their three-dimensional space. And so we're going to start with family 2. And family 2 has another name, and it's called linear. So if you're looking on your reference sheet, it's that first one. So family 2 is family linear. And what it's saying is there is a central atom, and then it has 2 lone pairs. And so how many things are around it? There's 2 things. And if we're talking about valence shell electron pair repulsion theory, we're thinking of those as those lone pairs. So right now, I'm just going to draw the lines. I'm not going to draw the electrons. All right, so the best arrangement for 2 things in three-dimensional space is 180 degrees apart from each other. That will give it the best distance from each other. All right, well, what if you have only one thing around it? Keep in mind there's still something here. No matter what you are going to do with 2 things, you only get 180 degrees. So go back over to the notes. And so what I'm talking about is if you have family 2 and 2 of them are bonds and 0 of them are lone pairs, you are in shape family linear. So 2 and linear means the same thing, but your overall shape or geometry is also linear, and the best angle is 180 degrees. So that's where I'm looking. That's what I'm talking about when I'm saying looking at the reference sheet. So I'm going to go back to the whiteboard. All right, so what are our options in family 2? So in family 2, we have 2 different things. And the first one is if they're both bonds, the angles come from bonds. And so that's 180 degrees, like we talked about. It's 180. And then the other option would be a bond and a lone pair. Now keep in mind that's still 2 things, okay? But this has one bonding and one non-bonding. So we're still in family 2 or family linear, and the shape is also linear. It gets more interesting as we get past family 2. All right, so let's go to the next variation. What happens if we have family 3? All right, family 3 is also called trigonal planar because literally it is a triangle in a flat plane. All right, well, what are the best angles for 3 things in 3-dimensional space? Those angles are all 120 degrees. All right, so that's the family, and that's its base angles. Well, what if you have 3 bonds. So if you have 3 bonds, 3 bonding, and 0 non-bonding, your family is trigonal planar, but your shape is also trigonal planar. Well, what if you have 2 bonds and a lone pair? Right? You're still in family 3. There's still 3 things around the center. So you have 3 bonding, not 3, 2. You have 2 bonding and 1 non-bonding. So you're still in family trigonal planar, but your shape this time only comes from the bonds. And so that shape is bent. Go back to the original. And this time I have 2 lone pairs and only 1 bond. Now there's still 3 things around it. So that begs the question, what is a thing? A thing is either a bond or a lone pair. Now remember, a single bond is one thing, a double bond is one thing, and a triple bond is one thing. So this has 1 bond and 2 non-bonding. So I'm still in family trigonal planar. But the shape comes only from the bonds. And so this is shape linear. So eventually you always get back down to linear. All right, so there's family 3. Let's look at family 4. All right, so for family 4, that is tetrahedral. Or 4 things around it. And the best arrangement for 4 things is not flat. So dash, dash, dash means behind, and wedge means coming towards you. So this is towards, that is behind, and these 2 are in the plane. And so basically it makes a tetrahedron, hence the name. So there's this face right there, and then there's this face, and then there's one back there, and then there's one at the bottom. So that is making a tetrahedron. So that's where the name comes from. And the angles are all 109.5 degrees. And it does not matter how you rotate it, it is 109.5. Now we draw it this way, flat, only for convenience. Okay, this looks like 90 degrees, but it's not. We only draw it flat for convenience. If you have family 4 or family tetrahedron, the angles are 109.5. So my variations, if I have 4 things, that's family tetrahedral. And if they're all bonds, the shape is also tetrahedral. If I have 1 lone pair, and then, now notice I can draw it different. That's still 4 things. 1, 2, 3, 4. It's still angle 109.5. It's still family tetrahedral, but the bonds are going to make the shape. Okay, so right there, they're making a triangle underneath. So it is shaped trigonal pyramidal, or a triangle pyramid, right? So that's with 1 lone pair. Well, what if there's 2? I'll put a lone pair here and a lone pair here, and that would leave 2 bonds. So again, I have 1, 2, 3, 4 things. And so my family is again tetrahedral. Therefore, my angle is 109.5, but my shape is only going to be dealing with those 2. So my shape is bent. And last but not least, what if I have 3 lone pairs and 1 bond? Well, guess what? I am still family tetrahedral, but my shape is only 1 bond, So my family is still tetrahedral. My shape is back to linear. My shape is back to linear. All right, so if we follow along, I'm going to jump back over to the notes real quick. If we follow along, what I've been doing is I've been going along, and here's the family. And then I'm asking how many bonds versus how many lone pairs. And then as you go across, it will tell you the individual shapes. So they're all the same family, but they have different shapes. And then this is the angle that goes with that family. And then here's just some examples of some different molecules. All right, we have two more families. We have family 5 and we have family 6. Now, the first time we have to worry about the family having a different shape in different locations is with family 5 and family 6. So pull that out. And family 5 is also called trigonal bipyramidal because it's two triangles that make pyramids sitting on top of each other. Their bases are touching. Now it's interesting on this one because I have to consider two locations. So I call this the axes. So just like on the Earth, for instance, like the poles, that would be the axes. And then I call this the skirt. So there's two very distinct locations. The angle between the axes is 180. The angle in between the skirt is 120 degrees. Okay, so those angles right there. But then if you look from the axis to the skirt, that is 90 degrees. So family trigonal bipyramidal, you actually have to know where you're talking about in order to tell me which angles. Okay, so those are the basics. And of course, if you have family 5 or family trigonal bipyramidal, and if they're all bonds, then the shape is also trigonal bipyramidal. Now, if you have one lone pair, again, you still have 5 things. We have 1, 2, 3, 4, and 5. So we're still family, trigonal bi, and we get the angles from the original. Then some of the names look a little odd. So we're going to go back. And so this one, I'm right here. So we're family 5. And if you have 5 bonds and 0 lone pairs, you would also be shaped trigonal bipyramidal. But if you have 4 and 1, it's seesaw shaped. And if it's 3 and 2, it would be T-shaped. And then we go back to linear. So I'm going to try and draw as best I can this seesaw shape and this T shape. It might not be very obvious, but let me see, how can I draw that better? Shape is going to be seesaw. Let me see if I can draw that better. Let me see. So I've got my lone pairs, and I've got one going back, one going forward, and then I have 2 out here. All right. If you can visualize with me, this is a seesaw. So this is where the person sits, and that's where the person sits. And so the reason it's called a seesaw is because that's how we visualized it. 1, 2, 3, 4, and 5. And that's where the name comes from. Erase this. And we're still in family 5. Only this time, we're going to have 2 lone pairs and 3. And again, we could put wedges and a dash and a wedge, or we could do flat and flat dash. Okay, as long as we get the idea of the axes and the individual skirt versus the poles, we're okay. Here, again, we're family 1, 2, 3, 4, and 5. So we're family trigonal bipyramidal. But our shape is only going to deal with these right here. And so if you'll notice, it kind of looks like a T. So it's T-shaped. And that's where that name comes from. So to the next variation, we're going to go to family 6. So family 6 is also called octahedral. It's also called octahedral. And for this one, you're going to have 1 in the center. You're going to have 2 in the axes. And you're going to have 1 behind, another behind, 1 at you, and 1 at you. And so basically it's making a little pyramid on each side, and those pyramids are stacked on top of each other for an octagon or an octahedron. And the interesting thing here is the axes, it's 180, but it's also 180 from here to here. And it's 90 from the axis to the skirt, but it's also between. So the only angles you have in an octahedron are 90 and 180. And then we can again go through all the variations, but I don't list them all for you. We're just going to do a few main ones. So if you have 2 lone pairs and 4 bonds, this would be family octahedral, but the shape only comes from the bonds, which looks like a square. And so that is called square ring. And that's the most common one for octahedral. All right. And then you can have one other. If you have 5 and 1, it's again a pyramid with a lone pair on top, which would be called square pyramidal. So again, there's more variations, but those are the only ones that we're going to play with. So that is called valence shell electron pair repulsion. So the family also give its angle. And so up through family 4, so this one, and this one, linear is always 180, trigonal planar is always 120, tetrahedral is always 109.5. But when you get to family 5 and family 6, there's actually 2 different locations. So you have to talk about, are we talking about the skirt? Again, that's a jolly term. Or are we talking about the poles? And so we have different angles. So this one has 90, 120, and 180. And then the family octahedral only has degrees of 90 and 180. And I have a picture for you. And so at the bottom here, these are just some pictures that I found that might be a little bit better than my drawings. And this is another variation that I have found. All right, so that is valence shell electron pair repulsion theory. One thing to note is electrons do tend to take up a little bit more room than others. So one interesting thing before we get out of valence shell electron pair repulsion is I wanted to point out water. Water has 2 lone pairs and 2 bonds. Now, technically, this should be 109.5 degrees, but these electrons, they repel each other, and so they squish those hydrogens in a little bit. And so this is more like 107 degrees rather than the 109. So again, family 4 generically has 109.5, but different things can, if you will, squish differently. All right, and that's going to take care of VSEPR theory for us. Until next time, jolly out.